Vážené dámy a pánové, je pro mě velká podsta, že jsem obdržel cenu Milana Odehnala za rok 2020. A chtěl především poděkovat České fyzické společnosti a členům poroty za vysoké hodnocení naší práce. A samozřejmě to je společnou zasluhou mých spolupracovníků a spoluautorů, především ze Slezské univerzity v Opavě a taky z jiných ústavů, z jiných zemí. Rád bych taky poděkoval organizátorům konference za milé přijetí a za možnost vystoupit a ukázat výsledky naší práce. Dal bych s vaším povolením pokračoval v angličtině, aby bylo to pochopitelné pro všechny, ale hlavně pro mě snadnější. So, good morning to everybody. It's a great pleasure to present the results of our work. So I will be speaking about some model of the possible explanation of the highest energy cosmic rays by the energy extraction from rotating supermassive black holes. So a few words about the cosmic rays. These are the phenomena that occur at very high energies. Basically, the energy of single particle can reach up to 10 to 20 or even 10 to 21 electron volts. Yes, so for the comparison, the largest particle accelerator that we have is LHC, is able to give like 7 orders or up to 8 orders of magnitude lower energies than the maximal energy at the cosmic rays. Yes? And due to these high energies and rareness of these particles, the physics, the mechanism of production and origin of these particles is still unknown. But few things that we know about these particles, that these are the charged particles, and we know the spectrum is here. It has some features like Ni at some certain energy, after which the flux of particles is decreasing sufficiently. And we also know that at high energies, these particles are extremely rare, so rare that, for example, those which have energy 10 to 19 electron volt, you may hope to expect 1 particle per square kilometer per year. And we also detect them on the Earth-based experiments, mainly when the primary cosmic ray enters the atmosphere, interacts mainly with oxygen, nitrogen, and creates a cascade of secondary particles, which all then falls in the form of air shower and can be detected on the Earth. And we also know that they are probably extragalactic at high energies because of the anisotropy in the arrival direction. So, how to create such particles? So if you're a theoretical physicist, you might like to look for the exotic scenarios, such as the extra dimension, Lorentz invariance violation, and so on and so on. But if you're an astrophysicist, you may prefer the accelerator models. But in order to accelerate the charged particle to such a high energy, you need to find a powerful source and take into account all the radiation losses, interactions, and so on. But if you want to build such an accelerator which will be able to accelerate particles to such energies with LHC technology, say with all these Tesla magnets, then you have to create the particle accelerator of the size of 400 million kilometers, which is equivalent to the size of Mercury's orbit. Yeah? So we thought, why not to try to tap this energy from black hole and transfer to single individual particle. So in order to see how it works, first we should look to the properties of the black hole. So nowadays, any astrophysical black hole is supposed to be Kerr black hole. It's supposed to be rotating. So this means that it is characterized solely by 2 parameters: its mass and the black hole spin. And black hole has event horizon and it has ergosphere, but I'm not going too much into details. But what is important for us that rotating black holes, the total energy of rotating black hole is larger than the total energy of non-rotating black hole. And this difference can reach up to 29%. Yes? So this means that most of the supermassive black holes, or most of the black holes in general, so up to a third of the total energy of the black hole can be extracted out. So if you will transfer it to electron volts for the standard supermassive black hole of 1 billion solar masses, you will get the available energy 10 to 74. So this is a tremendous energy. This means that the supermassive black holes are the largest energy reservoirs in the universe. Yes? So largest and the most compact. And the question arises how to extract this energy in the most efficient way. So first idea came in 1969 by Roger Penrose, who proposed some interesting mechanism, who noted that there is a special region which is shaded in blue in this picture. It is just above the event horizon. This region is called Ergosphere, where the particle's energy measured by observer at infinity can become negative. So this is not the proper energy of the particle, but rather the energy measured at infinity. So he thought that one may use this to extract the energy in such a way that you drop some particle into this region, which then splits or decays into two fragments. And if one of the fragments, say the particle 2, attains negative energy, then the third particle, respecting the energy conservation law, should escape from the black hole, from this region, with greater energy than the energy of the first particle. So this was the first proposal, but it wasn't so much efficient. The efficiency of this process was maximum 20%, and it was not astrophysically viable, and so on. There was some historical development of this idea over this half century. And, but if we want to explain these ultra-high energy cosmic rays, we need something like billion%. So that's how, that's what our model is proposing, basically. So first of all, we should say that any black hole is not only rotating, but it's also immersed into external magnetic field as any cosmic object, right? So this magnetic field around black hole can be generated due to dynamics of surrounding plasma, or it can be, say, binary system with a companion, say, magnetar or neutron star, and black hole can be immersed in it. But characteristic magnetic field for supermassive black holes is of order 10 to 4 Gauss. Yes? So 10 to 4 Gauss is 1 Tesla. Yes, so, but the question why the magnetic field parameter does not enter into space-time metric parameters like mass and spin, this is because the energy momentum tensor of the magnetic field is so weak that it cannot modify the gravitational background. Yes? So magnetic field is weak in a sense, but it cannot be neglected when you consider the motion of elementary particles, such as, say, protons or ions. And if you calculate the ratio of the Lorentz force to gravitational force, just some formally for relativistic proton, you will get something around 10 to 11, right? For standard magnetic field and the mass of the supermassive black hole. But also, so what we have now, that we have rotating black hole immersed into external magnetic field, and here, due to the frame dragging effect, magnetic field lines will be twisted. And twisting of magnetic field lines generates the electric field component. Yes? So it's quite similar to this classical, say, Faraday disk in physics. So basically, twisting of magnetic field lines generate electric field, which cause so-called selective accretion. So at the end of this story, the black hole accretes net electric charge. Yes. So any astrophysical black hole should have small electric charge, as well as actually most of the stars also have small electric charge, but in comparison with stars, black holes are compact objects, therefore the charge density will be much larger, and its effect can be non-negligible for the acceleration. So basically what we need, why I'm talking about the electric field, because this is electric field which can accelerate the particles, right? So this is how we create this electric field. Basically, this is created automatically if you have just any rotating astrophysical black hole immersed into external magnetic field, the electric field is generated. So then we can consider the ionization process, and for the simplicity, here I put the neutron beta decay. So simply we have a neutron that decays into proton, electron, and antineutrino, and we can place this decay close to the black hole, somewhere around the ergosphere. And the motivation for the existence of neutrons is straightforward, because usually the supermassive black holes are surrounded by accretion disks, which are very hot and very dense, and many nuclear processes occur in this disk. And that's how you generate neutrons, which then decay. And this decay, if you calculate then energy, you should write the energy conservation law, angular momentum, charge conservation, and so on, and you can calculate the efficiency. So final result is the following. So initially we have a neutron with a free energy of order of 10 to 9 electron volts. And after this process, close to the black hole, we obtain the energy of a proton near the supermassive black hole, the standard supermassive black hole, 10 to 9 solar masses and 1 Tesla or 10 to 4 Gauss. We obtain the energy greater than 10 to 20 electron volts. So this means that basically this gives a rise to interpret that this model as one of the possible explanations of the ultra-high energy cosmic rays. Here you can see the dependence of the energy on magnetic field for various masses, but what is important here also is the dependence on the spin of a black hole. So the spin dependence is not so crucial, which is very nice, because so it doesn't matter how fast the black hole is rotating. It's rather important that it is rotating and it is immersed into magnetic field. Yeah. So we can look more particularly to some particular objects. So the best known supermassive black hole candidate is the one located in the center of our galaxy. This is called Sagittarius A star. This is in the Milky Way center. We know its mass with very high precision. We know that it's most probably it's spinning. And if we calculate the same process for the galactic center supermassive black hole, we obtain a surprising result that the energy of a proton escaping from the galactic center should be of order 5 to 10 to 15 electron volt. Now, if you look to the spectrum of cosmic rays, you can see that this energy corresponds exactly to the location of the knee of the cosmic ray spectrum. What does it mean? So basically, this the sharpness of the knee. Well, usually knees are explained in the spectrum by the supernova explosion, but supernova is a catastrophic event, and this model gives some alternative explanation without the catastrophic events, and it also can, if there is a single source, the sharpness of the knee may indicate the existence of a single source. Then one of the best candidates for so-called pevatrons, yes, because this is 10 to 15 electron volt, is a galactic center supermassive black hole. Okay, so here are some constraints for the nearby objects. We know also that the cosmic rays at high energy cannot reach from very far from the location of our galaxy. By far, I mean the maximum distance is about 100 megaparsec. Right, so this is because of the interaction of the cosmic rays with the cosmic microwave background at cosmological scales. Therefore, we have to look for the supermassive black holes close to our galaxy. And there are actually many of such supermassive black hole candidates within the distance of 100 megaparsec, and with estimated masses. But the problem is that the magnetic fields are not properly estimated for most of these objects, but for some of them they are estimated. So we put them into this plot. So you can see there are few objects that possibly that can serve as possible source of the cosmic rays at certain energy levels. So this process works not only for neutron beta decay, but any kind of other ionization or decay processes. So I'm not going to go much into detail. So here is a numerical modeling. So we have to solve some complicated equation taking into account the radiation reaction, because since we have strong magnetic fields near the black hole, we have to take into account that there will be the synchrotron radiation of these particles. There will be also due to the synchrotron radiation, there will be back reaction, and you should do all this in the general relativity, taking into account the curvature of the space-time. And when you solve it, so at the end you end up with the following. So you have initially neutral particle revolving around black hole and say falling from the accretion disk toward the black hole, and where it splits into blue and red particle, and you can see that the energy of blue particle is increased like 100 times, because we actually, in the numerical simulation, we cannot put realistic values because the numbers will be too high, because in reality we are increasing energy like tens of billion times. So this is just to show that the process works, but what probably more important is to discuss the physics, why it happens. Actually, the physics is very simple. So as I already told, that we need electric field that accelerates the particles to high energies, but what does it mean? That actually you can transform this electric field to the charge of a black hole. So if you look to the picture as follows, if the black hole has, you can consider, you can solve these equations in two ways. So one, when you don't have a black hole charge, and second one with the same initial condition with a black hole charge, and you can see that the particles can escape from black hole with high energy only when the charge of a black hole is present. So this is very simple, I think. So you get, so you have some charged sphere, basically, not necessarily black hole. So I mean, just to understand the physics behind, right? So you put some neutral particle, because you cannot bring very close to the charged sphere the charged particle, because you have to overcome this Coulomb potential. But with neutral particle, there is no problem. You can come as close as possible as you want to this charged sphere, then split it into two charged fragments, and immediately these particles obtain, in addition to their energies, they will obtain Coulombic contribution. So one of them will be immediately fallen into black hole, and second one will escape into infinity. So the process is extremely simple, but from the general relativistic point of view. Yes, so also another advantage of this model is that we don't need to have this process in the ergosphere of a black hole. So as, for example, in the original Penrose process, the energy can become negative only inside the ergosphere, but in our process, it is not necessary. We can actually see that this process would perfectly work also on the far away. So this is accretion disk. So you can see on different parts of accretion disk, the particle is escaping, and dashed region is just this narrow cone along which the particle can escape. This can also serve as a possible, at lower energies and probably for electrons, serve as one power engine for the relativistic jets observed in many microquasars, black holes, AGNs, and so on. Yes, so here is a GZK cutoff. I a little bit already spoken about this. This is about the interaction of the cosmic rays with the cosmic microwave background. I'm not going to talk about this in much details, but we should take it into account if we want to see the transport of the cosmic rays. But we should also take into account the radiation losses. So if there is a magnetic field, say galactic magnetic field, which is 10 to minus 5, then there are some distances over which the particles lose significant amount of its initial energy. And here is a summary. Yes, so basically I have shown one of our models which tries to explain the highest energy cosmic rays by the energy mining, by the energy extraction from supermassive rotating black holes. And for this, we need just two ingredients. We need basically rotating supermassive black hole, magnetic field with magnetic field, and we should consider ionization. Everything else works like more like an automatical regime. And there are many advantages of this model, but I would rather speak about the future prospects, that we would like to go further with this model, more into the observations, into the statistics and the spectrum. So this is our goal. So I think I'm in time. Yes. Thank you very much for your attention.
Could we discern between these two explanations?
Yes, I think the GZK cutoff is crucial when you are where we are speaking about the protons or ions in ordinary of the ordinary matter, and probably it makes no role when you're considering exotic scenarios or existence of new particles. Yes, so here we are considering the acceleration mechanism. So for this we consider just simple protons basically, or ions for which GZK cutoff should be present. Yes, so we think that this is we are more like in astrophysical direction rather than this
Thank you.
exotic.
Thank you very much. And now questions from the auditorium. Any? Okay, fine.
I would like to ask, okay, the particle comes to that special part of near the black hole, and it decays there. There is some physical mechanism which accelerates the probability of decay in that special case, or it is just random. I don't know, maybe some time dilatation or something makes the decay more probable.
Yeah, you can consider this, but actually it's not so important, because I mean, if you once you generated neutron and in huge amount, eventually some of these neutrons will decay, right? So yes, you can consider the probability and calculate it, but we haven't gone so far from this point of view. But eventually any neutron will decay at some point, so we just have shown that if such a process occurs close to black holes, then the proton should escape. I also probably had to say why proton is escaping, why not electron, because this is because of the orientation of the electric field lines in such a way that you can consider that the black hole is more likely acquiring the positive charge. Why? Because first of all the matter rotating around black hole in the ergosphere, it is co-rotating, so which gives certain alignment of magnetic field lines, which is generated in the plasma. Yes, so it will be aligned along the magnetic field line. It will share the symmetry of the background space-time. It will share the symmetry of black hole. Therefore, it is more likely that these are the protons which are escaping.
Is it possible to say something about angular distributions of these high energy particles? I mean, I'm asking because we are seeing black holes which are having jets coming from some pole regions. So
yes, it's a very good question. It depends on the energy that this particle is obtaining from this process. I would say that actually you can consider, since you have accretion disk, you can consider this process everywhere at any point. So initial angular distribution can be arbitrary, basically. I would say isotropic, but you have magnetic field lines, yes, and there is a tendency for particles to escape along the magnetic field lines. So there will be, of course, more particles of the high energy which will escape along the field lines, and if you are able to see the geometry of the magnetic field, then you can also calculate this angular distribution and the flux in particular direction of this cosmic rays.
If there are no more questions, I would like to thank you again.
Yes. Thank you very much.